and now we'll move on to step 7, determining the number of ventilators in the reservoirs. There are a number of factors that must be taken into account when carrying out this step, so let's look at the first factor. It must be ensured that the exhaust capacity provided is at least the natural or mechanical exhaust rate that is required. If the installed capacity is greater than the required capacity, then the base of the smoke layer will simply remain a little higher in the reservoir. For natural ventilation, the required exhaust capacity will be a specified area of ventilation, and for mechanical, it will be a volumetric flow rate. In the last step, step 6, we calculated required ventilation areas and mechanical extraction rates, and now let's suppose, for example, that we need 12.6 square metres of aerodynamic free ventilation per reservoir. Let's look at how this can be provided. It cannot be provided as a single ventilator, as ventilators don't generally get made that large. An aerodynamic free area of, for example, 12.6 square metres equates to a geometric area, or an actual measured area, of 12.6 divided by 0.6, which equals 21 square metres. We've used the figure of 0.6 here, or 60%, as the coefficient of ventilation, and we do this because the ventilators are not 100% efficient. So how big are ventilators? Well, they're not normally larger than about 6 square metres in geometric area, with dimensions not normally exceeding 3 or 4 metres in either direction. As mentioned earlier, to determine the effective area of a vent, otherwise called the aerodynamic free area, it's necessary to multiply the geometric area by the coefficient of ventilation, which is usually about 0.6 or 60%. Therefore, something of the order of 6.25 times 0.6, which equals 3.75 square metres, is the largest aerodynamic free area of a vent that would be expected. So one step in determining the minimum number of vents required can be by dividing the required total aerodynamic free area required for the reservoir by the aerodynamic free area of the chosen ventilators, and then rounding the figure up. In our example, where we needed 21 square metres, if the designer wants to use ventilators with an aerodynamic free area of 3.7 square metres each, then we divide 21 by 3.75. This equals 5.6, and we round this up to tell us that we need 6 ventilators. So we need at least 6 ventilators as a minimum in each reservoir, but we may require more if other criteria, such as plug holing and stagnation checks, are not met, and we'll look at these later. Let's look at another example. Let's assume we have a total aerodynamic free area requirement of 24 square metres per reservoir. What's the minimum number of ventilators, each with an aerodynamic free area of 2.5 square metres, required to satisfy this? Well, 24 divided by 2.5 is equal to 9.6, so we round this up to tell us that we need 10 ventilators in each reservoir. Now you should try the few exercises to make sure that you're confident with this technique. Don't forget that this is the minimum number of ventilators and that more might be required due to other checks. There are some advantages to having a larger number of smaller ventilators rather than a fewer number of larger ones. The smoke won't have to travel so far to reach the nearest ventilator, so will remain hotter and more buoyant. Also, the smoke leaving the ventilator is less likely to entrain air from beneath the smoke layer into its flow if it's leaving via a smaller ventilator. It's up to the designer to choose the ventilators that are to be used. The choice also has to consider the aspect that the ventilator will have when in situ. That is, the ventilators may be situated in a flat roof, or they may be situated in a pitched roof, or they may be situated in a vertical part of a building such as a wall. That covers the first step in how to determine the minimum required number of ventilators for natural ventilation,